All right, so last time around, I totally forgot to actually finish out and show that if you take a second difference in the general quadratic case, you'll end up getting a constant value. I did show it with the numbers, and hopefully if you watched that video, you kind of said, hey, what about this column? And then kind of did it yourself and said, well, 3a plus b minus a plus b would give me 2a. 5a plus b minus 3a plus b would give me 2a, and so on. So anyway, if you were to try it yourself with like a cubic, you'll notice that it ends up taking 3 differences, 3 times of doing this differencing process. And that constant that you should get in that case is 6a. That's the cubic case. Here, the fact that we get 2a, this is all very reminiscent of, not reminiscent, what's called foreshadowing, the opposite of reminiscent, of what's going to happen in our future, which is we're going to be taking derivatives. And it turns out that if you take 2 derivatives of something like x squared, so the first derivative would be 2x, and the second derivative would just be a 2. And if you had an a in front, then you'll have a 2a. If you were to take 3 derivatives of something that looks like this, then the first derivative begins with a 3at squared plus other stuff. The next derivative would be a 6at, and the final last derivative would just be a 6a. So anyway, this is all kind of stuff that we're going to see again in our future, which is part of why I go beyond and talk about these other interesting facts. But let's talk about exponential growth. This is much more applicable to what we're going to do a lot of in this class. And instead of growth, I could also say decay. Okay, exponential change. I don't know. All right, so here's some common doubling times for various bacteria. And man, I had no idea that E. coli was so aggressive. It only takes 17 minutes to double. But granted, doubling times, these are going to be slower in the body. So all of this is done in optimal conditions, and our body is not optimal. All right, so nonetheless, we can start to make it more. So let's suppose that I had some E. coli, okay? And the amount that I have is b sub t. Time t, and let's suppose that it's under optimal conditions, and I begin with my initial condition, my b sub 0. 17 minutes go by, and that's when I'm going to take my next measurement. And since 17 minutes go by, that means my b sub 1 has, well, we know what it's going to be. It's going to be 2 b sub 0. And another 17 minutes are going to go by, and I'll take my next measurement. And b sub 2, we know that that's going to be twice b sub 1, but I could expand that out even more, and I could say, well, this is 2 times 2, b sub 0. And 3, so another 17 minutes go by, b sub 3, it's going to be 2 b sub 2, but that's 2 times, and now I'm just going to use this form here. So in fact, that's 2 times 2 times 2, b sub 0. That goes by a different name, which is 2 cubed b0. And in fact, I could have written the one above as 2 squared b0. And I'll do one more. b4 is 2b3. And if I were to kind of write it all out, I would end up getting 2 to the 4th b0, right? It's just 2 times that previous value. Okay, so in general, well, we'll get there in just a moment. Actually, let's describe the updating function for this discrete time dynamical system. The next measurement of bacteria is twice the population of the current measurement of bacteria. That is the updating function. In general, for something that ends up being exponential, you might have something like b sub t plus 1 is equal to some constant multiple times b sub t. So in this case, I'm using 2, and generally you might have c. Okay, just to connect this with the previous video, if we were to attempt to do the discrete differences, let me get rid of all this information. And let's try and do discrete differences and see what happens, okay? So if I were to do the first difference, that means I take b1 and I subtract b0. So b1 minus b0, but hey, b1, that's 2b0, So really, I have 2b0 minus b0. I have 2b0 minus b0. I just have b0. Now if I do b2 minus b1, that's 2b1 minus b1. That's just b1. And then I do b3 minus b2. Well, that's just 2b2 minus b2. That's just b2. Okay, so the phenomenon that we're witnessing right now, let me clean this up to make it more clear. When I do the computation of b sub t plus 1 minus b sub t, well, in this case I have b0, in this case I had b1, in this case I had b2, in this case I had b3. My difference column looks identical to my beginning case. And depending on your constant c, you might not look identical, but you're never, no matter how many differences you do, you're never going to get to a constant the way we did in the previous video. And this is what happens with exponentials. Okay, so that's just kind of a remark. Let's write back down, we have our updating function. Let's find the solution function, and let's just do it for the general case, okay? So in general, I have t, and I have bt, and at 0, I have b0. And now I'm in the general case, so here's my updating function. So the next time unit, I have cb0, and the next time unit, I do c times that, well, that's c squared, b0. And the next time unit, I do c times that, that's c cubed, b0. And hopefully you see the pattern. At time t, I have c to the t, b0, and that will give me b sub t. Okay, so here's a solution function. So there's two solution functions you're expected to know. One of them was the linear case way back from the first video. Let me see if I can pop back up there really quick. All right, so linear case is when we just keep adding a constant. And the solution function in that case was a line. And where do I have you? I mean, I have it here. It's all messy. Anyway, you can go back and watch that video. So that's one of the solution functions we're supposed to know. The other solution function is this exponential growth or decay. So when your updating function is a constant multiple, right? So the other one we saw was a constant addition. This is a constant multiplication. Then your solution function is exponential, right? With that constant to the t, and then your initial condition here. All right, but life is never that clean. And what do I mean by that clean? It's almost never just a c multiple, or it's almost never just a c addition. So let's look at something that is more realistic, and we'll connect it to the next topic of the course, which is stuff like equilibriums and cobwebbing and all that. So, okay, let's say I want to take some Tylenol. Tylenol is acetaminophen, and it has a half-life of like 5.5 hours, but I'm just going to call it 6 hours to make this math easier. And you've got dangerous amounts of Tylenol in your blood if you have 4,000 milligrams or more. Typically, extra strength Tylenol is 500 milligrams, and you really shouldn't take more than 8 of those in any 24-hour period, or else you're getting into the danger zone. So, let's say we've got a patient, and they're in some pain, so they're taking 1,000 milligrams of acetaminophen, whatever, every 6 hours. And maybe this is before... excuse me. Anyway, this patient, are they at risk of overdosing? If they take 1,000 milligrams of acetaminophen every 6 hours for the rest of their life, are they at risk of overdosing? So let's go ahead and get a discrete time dynamical system for the amount of acetaminophen in their body. So the variable a sub t, it's going to be, you can take out the word measure, it's the amount measured in terms of thousands of milligrams of acetaminophen at time t, where t is the number of 6-hour intervals. So this patient, they take 1,000 milligrams. So there's my initial condition. All right, 6 hours later, they're going to take another 1,000 milligrams. So they take it, but they have a residue of acetaminophen in their body. The 6 hours have gone by, so one half-life has gone by, So the amount that was there gets divided by 2. And this is the new total amount, right? The old amount plus the new pill. Okay, well, 6 more hours go by, and the amount that was in their body goes through a half-life, and then they take another pill. So that's the new amount in their body. And hopefully you can kind of see the pattern. The updating function is a sub t plus 1 is equal to 1/2 a sub t plus 1. And I just want to point out this plus 1 is in the subscript, this plus 1 is not. And that's very different. All right, so we have a model now. Here it is. And we're curious, is this patient going to overdose? All right, so let's go ahead and try and answer that. So one way to answer it, we can just crunch the numbers. All right, so let's see if when I type it shows up. It doesn't, but it will show up when I hit enter, so that's nice. All right, so I can have Excel just kind of generate a bunch of time increments for me. So these are all in 6-hour units. So T is in 6-hour chunks, all right? And then this is the acetaminophen, and this is in 1,000 milligram units, okay? And there's a way to have Excel do updating functions for you. I can't remember if I released a full video or a comment to everyone video, or if I just made a short one for something else. But the way it's done is you kind of hit equal sign first, and then you can reference a cell. And oops, I don't want this. I want. Okay, great. So I'm having Excel. Let's see, can I point on here? Can I do? No, I can't. All right. So what Excel does is it takes the value in this previous cell, it multiplies it by 1/2, and it adds 1, and that's what it puts in this next cell. And I'm just going to have Excel do that for me over and over again. So here we go. Boom, done. Right? If I if I multiply 1.5 by 1/2, that'll give me 0.75, and if I add 1, there we go. And so Excel just does it over and over and over and over and over. All right. So let's see. 15 of these 6-hour chunks have gone by, and it doesn't look like I'm at risk of overdosing. In fact, it looks like I'm approaching some kind of constant value, right? If I continue to take 1,000 milligrams every single 6 hours, it looks a lot like I'm approaching 2. Hopefully you all agree. And in fact, if I do this far enough, let's see, if it happens really easily, I'll just do it. But Excel might just say, you know what, screw it, I'm going to call it 2. Yeah. So there you go. Now it just never changes. Even though every single time, Excel, in fact, you can see it down here. What Excel is doing is taking the cell above, multiplying by 1/2, and adding 1. That's what it's doing for me. And in doing that, it just generates this whole list. And eventually, once it hits 2, it just stays at 2. Right? So if this patient or myself or whatever had 2,000 milligrams and I continue to take 1,000 every single 6 hours, it looks like I just stabilize. Okay. So this is one way to answer the question of what is the long-term behavior. It's just to generate a bunch of data and hope that we can see a pattern. But humans are not great at numbers, and so we kind of got lucky with that. So what's another way to see this stabilization happens? Or equilibrization. Anyway, what we've hit in this case is called an equilibrium. So the other method is cobwebbing. All right, so there was another video that was linked in the announcements where someone talks about cobwebbing. Let's just do this example real quick. So what I want to do is plot my solution, or not my solution, sorry, my updating function. So I want to plot this. All right. So, okay, let's go on down here. Boom. Going over. Sure. And I have a y-intercept of 1, so I'll say it's here. And a slope of 1/2. Okay, 2, 1, 2, 1, sure, and then 2, 1, 2, 1. Okay, this is good enough. Boom. Okay, great. So there's my updating function. Now, we also want to plot the equilibrium state. And I'm going to put my dog outside. All right, go for it, bud. All right, so we want to plot the equilibrium state. An equilibrium state is when the amount that you're measuring stops changing. So that looks like this. The amount of acetaminophen in my body at time t is the same 6 hours later. And you can kind of think of this as the line y equals x, because indeed that's what I'm going to plot, because my horizontal axis, my input, is a sub t, and my output is a sub t plus 1. Okay, so what, let's get this line up here. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I can kind of throw this up like that. Boom, there we go, great. Now, the way cobwebbing works. So first off, my input is a sub t. It's just some measurement, and I'm going to start at the initial condition, but in general, if you want to use an updating function in a plot, you don't have to start there, but let's go ahead and do it. So I'm going to pretend each of these dots is 500 milligrams. So right here is 1,000 milligrams. So this is my a sub 0, and I'm going to plug that into my updating function. Here we go. And my updating function, if I input a sub 0, my updating function will output a sub 1. Okay, that's what the updating function does. It just tells you the next measurement. So, all right. There we go. Now, the very slick maneuver to try and figure out A2, based on this picture here, is to travel horizontally to the line y equals x, or to what's really, so this is an equilibrium line, and that's when the amount of substance at time t is the same at the future time, right? Okay, and if you think about what this is saying, right, if this was ever true, like for example, say it happened at t equals 10, then that says A10 is equal to A11. But the moment it's true, there's nothing special about my t value. So then it has to be true for T11, which means this is equal to A12. And then it has to be true for T equals 12, which means this is true for it equals A13, and so on and so on and so on. You just get stuck. And that's what we saw on the spreadsheet that I showed. Okay, back to cobwebbing. So cobwebbing, I move horizontally. And when I move horizontally, that means I fix a y value. Okay, so here we are. My y value is fixed, which means my y value is unchanged. It's A1. But I'm sitting here on the line y equals x, which means my x value has to equal my y value, so it's also A1. So this slick maneuver lets me find A1. Not that I ever actually have to plot it here. I don't really care about that. But it lets me find it on the input axis. And so then I can input it into my updating function. And now this point here, its x value is A1, its y value is A2. Its y value is A2 because that's what the updating function does, right? If you give me an AT, it gives me an AT plus 1. Okay, and now I repeat this process. So I go over, and now this point here, its y value is the same. So that's an A2. But it's, since it's on the line y equals x, its x value is also A2. So this is A2, A2. And then I can put that in my updating function, put that here, and put that here, and put that here, put that there. And it'll kind of get bunched up, and then it gets stuck right here. It gets stuck at this intersection point, which is called an equilibrium. Equilibrium. The equilibrium happens when your updating function, so in this case, a sub t plus 1 equals 1/2 a sub t plus 1. When that equals the equilibrium state, which is a sub t plus 1 equals a sub t. So when both of these are true, oops, that's when we found an equilibrium point. And cobwebbing will reveal whether or not you travel towards that equilibrium point or you travel away. And those are the notions of stability and instability, or unstable and stable. Okay, so let's say we cobweb like this, and then I'm curious, okay, it looks like I'm heading toward an equilibrium. What is that equilibrium point? Well, an intersection point of two graphs is when they're both true, so I can kind of set them equal to each other. But what I mean is, look, here's one copy of AT plus 1, here's another. And I can kind of just say, well, if this equals that, which equals that, which equals that, I'm just going to equate these two right-hand sides. And I have a sub t is equal to 1/2 a sub t plus 1. And now if I solve for a sub t, what do I have to do? I have to subtract 1/2 a sub t from both sides. And that gets me 1/2 a sub t is equal to 1. And now I have to multiply both sides by 2 times 2 times 2. And that says a sub t is equal to 2. And this is exactly what we saw in the Excel spreadsheet. The amount of acetaminophen in my body approached 2. That was my equilibrium state. And in fact, if I were to plot all these points, then I began with 1, 1.5. All right, 1 second. I'm going to grab my dog again. Wait. What? All right. So, cobwebbing, we never had to see any of the numbers, even though I was just about to jump back to connecting everything. But let me just say this. All these numbers that we see on the Excel sheet would be the y values of this iterated movement. So let's see, 1, 1.5, 1.75, 1.875. All right. So if I were to look at this first y value, this would be 1.5. This next y value would be 1.75. This next y value would have been the 1.875. And so on and so on and so on. So like this gets really bunched up here approaching the equilibrium, the same way the Excel sheet got really bunched up approaching 2, which was the equilibrium. Okay, so that's an example of cobwebbing. The equilibrium point is what happened when both of these equations were true. We can solve for the equilibrium point by kind of ignoring this value and setting these two sides equal. So that's what I did here. And then you solve, you say, hey, what might my a sub t be? What is this value for equilibrium? And since when I did this cobwebbing, I kind of traveled, so up and towards and up and towards and up and towards. Since I traveled towards equilibrium, we would say this equilibrium is stable from the left. I say from the left because I started over here, which was to the left of my equilibrium state. Okay, I'm getting ahead of myself, and that is good for this video, so I'll see you next time.